What is string theory? String theory is a theoretical framework that aims to unify all of the fundamental forces and particles in the universe. It is considered one of the most promising candidates for a theory of everything, a single, overarching framework that can explain all physical phenomena. At its core, string theory proposes that the fundamental building blocks of the universe are not point-like particles but rather tiny, one-dimensional, strings. These strings are incredibly small, on the order of 10 to the power of -33 centimeters, and vibrate at different frequencies, giving rise to different particles and forces. String theory has its roots in the early 20th century, when physicists began to study the behavior of subatomic particles. The discovery of quantum mechanics in the 1920s revolutionized our understanding of the universe, but it also introduced new problems and contradictions that could not be explained by existing theories. In the 1960s, a group of physicists including Gabriele Veneziano and Yoichiro Nambu independently developed a mathematical model that described the strong nuclear force in terms of one-dimensional objects called strings. This model was refined and developed over the following decades by a number of physicists, including John Schwartz and Michael Green, into what we now know as string theory. One of the key insights of string theory is that it can potentially unify the four fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces. In traditional physics, gravity is described by the theory of general relativity, while the other three forces are described by the Standard Model of particle physics. These two theories are incompatible with each other, and attempts to merge them have so far been unsuccessful. String theory proposes that all of the fundamental particles and forces can be described in terms of the vibrations of one-dimensional strings. These strings can vibrate at different frequencies, which correspond to different particle masses and energies. In this way, string theory can potentially unify all of the known particles and forces into a single, coherent framework. Another key feature of string theory is the concept of extra dimensions. In traditional physics, there are three spatial dimensions: length, width, and height, and one temporal dimension, time. However, string theory predicts the existence of additional dimensions beyond these four, which are curled up and hidden from our direct observation. The number of extra dimensions depends on the specific version of string theory being considered. For example, bosonic string theory predicts 26 dimensions, while the most widely studied version of string theory, known as superstring theory, predicts 10 dimensions. The idea of extra dimensions is not unique to string theory. Other theories, such as Brane world theory, also propose the existence of extra dimensions. However, string theory is unique in its ability to predict the properties of these extra dimensions and the effects they would have on the observable universe. One of the challenges of string theory is that it requires a mathematical framework that goes beyond traditional quantum mechanics. In traditional quantum mechanics, particles are described by wave functions, which give the probability of finding a particle in a particular location. However, in string theory, particles are described by the vibrations of strings, which are more complicated objects that require a new mathematical framework. This new framework, known as conformal field theory, is based on the idea of symmetry. Symmetry is a fundamental concept in physics, and refers to the idea that a physical system remains unchanged under certain transformations. In conformal field theory, the symmetry transformations are based on the geometry of the string itself, rather than the geometry of the space it is embedded in. Another challenge of string theory is that it is currently impossible to directly observe strings or the extra dimensions they predict. The strings are incredibly small, smaller than the Planck length, which is the smallest length scale that has any meaning in traditional physics. As a result of the small size of strings, they are predicted to have effects on the universe only at very high energies, which are not currently accessible to experimental physics. However, some indirect evidence for the existence of strings and extra dimensions has been proposed. One such proposal is the existence of gravitons, which are particles that carry the force of gravity in string theory. Gravitons are predicted to exist in string theory, and their existence could potentially be detected through experiments such as gravitational wave observatories. However, no direct evidence for gravitons or the extra dimensions predicted by string theory has been observed to date. Despite these challenges, string theory remains one of the most active areas of research in theoretical physics. One reason for this is that string theory has a number of attractive features that make it a promising candidate for a theory of everything. One such feature is its ability to potentially unify all of the fundamental forces and particles into a single, coherent framework. This would simplify our understanding of the universe and potentially lead to new insights into the nature of the cosmos. Another feature of string theory is its ability to potentially resolve some of the outstanding problems in traditional physics, such as the incompatibility between general relativity and the standard model of particle physics. String theory has also been used to propose new ideas in cosmology, such as the concept of inflation, which proposes that the universe underwent a period of rapid expansion in the moments after the Big Bang. However, string theory is not without its detractors. Some critics argue that it is not testable or falsifiable, meaning that it cannot be proven or disproven through experimental observation. Others argue that it is overly complex and requires too many unproven assumptions. Despite these criticisms, string theory remains a fascinating and active area of research in theoretical physics. It has already led to new insights and ideas in our understanding of the universe, and may continue to do so in the future. Only time and further research will tell whether string theory will ultimately prove to be the correct framework for describing the cosmos.